Thank you for coming to today's Jones Seminar. It's really a pleasure to have our speaker, Professor John Vetelino from University of Maine here to speak to us. He's a professor of electrical and computer engineering. He is, I think, must be one of the long-standing citizens of the department at University of Maine. He received his bachelor's, master's, and PhD in 64, 66, 69 from the University of Rhode Island, and moved up, right after his PhD, it looks like, moved up to the University of Maine, where he is currently a professor of electrical and computer engineering. He founded the Laboratory for Surface Science and Technology at University of Maine and is currently the leader of the solid-state sensor group there. His research group is working on chemical and biological sensors based on acoustic waves and chemo-resistant technology. He has done stints at different institutions, once at the Max Planck Institute in Stuttgart. I can't pronounce the name of that institute. That's a complex German name. Working on solid-state properties of piezoelectric crystals. He also went and was a Presidential Research Achievement Award winner at the Outstanding Researcher Community at University of Maine. And from 83 to 87, he was chairman of the Electrical Engineering Department. He received the Distinguished Maine Professor Award in 2008 and is an IEEE Fellow. He has given several invited talks, many papers published, invited papers, over 200 publications total, received outstanding paper awards, and guest editor for a number of journals. Member of the Technical Program Committee of the IEEE Ultrasonics Group and a steering committee member for the International Chemical Society's Sensors meeting. So it's really a pleasure to have him come over today. I should also say he partly trained our own professors, John Zhang, as a master's student several years ago at University of Maine. And so it's nice to have that connection between Dartmouth and University of Maine. He'll be talking about lateral field excited acoustic wave sensing. So thank you.
What I've tried to do here is, perhaps after I met with everybody, I would probably have made the talk a little bit more general than what I have. But it is basically a specific talk focused on a lateral field excited acoustic wave sensing platform, one that was patented and developed in my laboratory. The talk is divided into several categories. Initially, I'll talk about what I call a sensor system, which in the view of many people is different. Surface-guided acoustic wave platforms, bulk acoustic wave platforms, and then begin to focus on the quartz lateral field LFE sensing platform and talk about coupling coefficient, which relates to the amount of energy that's transmitted or transferred from the electrical signal to the mechanical wave, the curvature of the crystal, the equivalent circuit for this platform, the impedance spectra of the platform, liquid properties, conductivity, permittivity, viscosity, equivalent circuit models comparison between the theory and experiment, and then a little bit on chemical sensors, work that we've done, biological sensors, explosive sensors, and then finishing up in terms of talking about another kind of material used in lateral field excited sensors, basically lithium tantalate sensor platforms, the so-called temperature compensated shear mode, which I'll talk about in a few minutes, its coupling coefficients, its liquid properties, and finally conclusions, and then some comments of what might be ongoing work and future work in this area. First of all, when you look at a basic sensor system, people often begin to focus on one particular aspect. They might focus on the sensing element, obviously, because that's the entity that you're out to sense, or they might talk about the target selective recognition element. In other words, these two in combination, one with the other. My focus is the biosensing platform, and I could have written this as chemi-sensing platform, which embodies, to a large extent, the quantity sensitivity, whereas this one, a quantity selectivity. Now, the actual block diagrams over here are very important and are often totally ignored in sensor systems, and that is the actual sample preparation. In other words, the target analyte that you're out to detect can be located within a gaseous environment, can be located in a fluid environment. The question is there any way in which, before you expose it to the actual sensing element and platform, etc., can you massage the medium? How can you massage it? Maybe by particulate filtration, if you're looking at the determining particles of a particular size, maybe some biofiltering, and maybe some incubation if you're talking about biological entities to detect. So when I look at the whole thing, I like to look at it as an entire biosensor system, and again, this is where my focus is the actual platform itself. Surface-guided waves, the most common ones are the surface acoustic wave, which is this one here, where the wave is an acoustic wave propagating on the surface of a piezoelectric material, but that's certainly not the only one. Acoustic plate modes, where the actual piezoelectric material is a plate, and the acoustic wave bounces off of the bottom and the top of the plate. Shear horizontal, which is a special kind of surface acoustic wave in which the displacement components are polarized in the plane of the crystal itself. Love mode, which is an actual mode that occurs in the actual film itself, which is detecting the analyte of interest, and that film, of course, is on top of the piezoelectric substrate. This is more or less analogous to an electromagnetic waveguide. Flexural plate mode corresponds to the actual plate moving back and forth, much lower frequencies than some of the top ones. And then a thin rod or cantilever, which is a piezoelectric material excited to vibrate back and forth, and its vibration turns out to be indicative of what's being placed on it. The bulk acoustic wave platforms, electromagnetic acoustic transduction sensor platform, those people who have been in electromagnetics in many years would realize what this particular platform is. It was used as early as in the 1950s. Another kind of bulk wave platform called the MOS, and I'll go into a little detail on that, and an electromagnetic piezoelectric acoustic sensor platform. And you might ask the question, well, where in the world is the lateral field excited one? It's coming. The monolithic spiral coil, quartz crystal magical balance, small electrode geometry, and finally, the one that we're focusing on is the lateral field. So that when we speak about acoustic wave platforms, we're not talking basically one or two or three. There's been a whole combination of them that have been published in the literature. The so-called EMAT platform, basically it consists of two magnets on the top. Those magnets have a coil underneath them. The magnets are here, the coil here. That sets up eddy currents in a conducting material down here, which via the Lorentz force, remember IDL cross B, generates a force which can be manifested as longitudinal or shear waves. This one here, the magnetic resonance or MOS platform, more modernistic version of the earlier one, consisting of a magnet, hand-worn spiral coil, a conducting layer, and again, the current in this hand-wound coil sets up eddy currents here, and then here's the magnets to set up the acoustic vibrations in the sensing substrate. This particular kind of a configuration utilizes a piezoelectric material, or it can be a regular material, non-piezoelectric, and the previous one here, this one here can also be a non-piezoelectric material down in this region. Finally, the so-called MPAS platform. The coil is separate from the substrate. It almost acts as an antenna. And this material is the piezoelectric substrate, which is often 18-cut quartz. And then finally, the so-called MISCAT, one that we've done a lot of work on at the University of Maine and published several papers, where we have the actual coil deposited onto the piezoelectric substrate to excite the the bulk acoustic wave. All right, the common material that we use, AT cut quartz. This is the X, Y, and Z coordinates in the crystallographic orientation, and this is the rotated, single rotated angle, minus 35.25 degrees. This material is very attractive. With electrodes on the top and bottom faces of this material, it will excite a perfect transverse shear mode with displacement components that are basically transverse to the direction of propagation, and further, that temperature transverse shear mode is temperature compensated, which essentially means that its properties don't change as a function of temperature, and that is important in sensing. The top view of the most common device made on this quartz substrate is the standard QCM, which is often referred to as a quartz crystal monitor. That's what QCM stands for. The shaded and dotted regions are gold. This is on the top. These are on the bottom of this sample. And believe it or not, the actual electrode goes around the side of this sample to connect to the electrodes on the back side. So what you have here can be excited on the back side of the crystal with an RF signal, and it then sets up a transverse shear mode that propagates from the top face and bottom to bottom face of this material. This particular QCM is a standard device that's used in thin film deposition systems, where you're depositing a thin film onto a substrate, and that thin film on that substrate corresponds to a particular device for which the thin film's thickness is an important parameter. So what you do is you have this particular device in concert with the actual device that you're doing, and the frequency of this device changes, and as the frequency of this device changes, it's indicative of how much mass is onto that device. And if you know the density of the material you're depositing, then you'll know the thickness of what that film is, and that's an critical parameter in the deposition system. We started with that, and if you notice on that QCM, you basically had metal on the surface. So if you wanted to put a analyte selective film on that surface, and the analyte selective element, or the analyte that came down, basically change an electrical property of that film, you would never be able to measure it because you got an electrical short on the surface. So what we decided to do was to very simply say, let's try to remove that. And we went through various perturbations. First perturbations are, let's just put a tiny dot on the top and see what we get. And then we played around with a ring, and then we decided to open the ring, and it gives you some various perturbations that we looked at there. And then finally, we said, let's take the whole thing off, and let's put the electrodes on the bottom. This represents that same cut of AT cut quartz, and this is the bottom face, and this represents the electrodes. And as you can see here, these electrodes form a half-moon type structure. And this psi angle here is a very important factor as far as the device itself is concerned. Now, with the electrodes on the bottom, the fundamental question was, can this so-called lateral field, which essentially comes about by applying a voltage across that electrode configuration, which results in an electric field that is in the plane of the crystal as opposed to the QCM, which is in the thickness of the crystal, can that excite the same transverse shear mode? And here are the actual calculations on that. This is that psi angle that you saw in that previous slide, namely this angle right here. And what that indicates is that if you're 90 degrees away, or minus 90 degrees away, the coupling to that transverse shear mode, which is given as mode C, is finite, and the coupling to the other two allowed bulk acoustic wave modes, the longitudinal and the other shear, is 0. Over here, a similar sort of situation. So it basically says, yeah, you can put those electrodes on there, make sure that they're oriented so that the electric field is either plus or minus 90 degrees. Further than that, we went ahead and we fabricated that device, and we proceeded to go ahead and characterize it, and we did not get the responses that we expected to get. We went back to the quartz crystal monitor and we began studying it very, very carefully, and what we found out was that the quartz crystal monitor did not have a bottom surface that was parallel to the top surface. In fact, one surface was like this, the other surface was planar convex. And this came about from very careful examinations. People have been working on quartz crystal monitors since the 1950s, and this was one of the trade secrets that they did not give away. If you really dug in the literature, you could see it. Before we even dug in the literature, we did some examinations of the surface and determined that in the QCM it was planar convex. So what did that mean? It meant the following. This represents the planar information, and you see the excitation. This is the absolute magnitude of the impedance. This is the corresponding phase. You get a very tiny value over here and a tiny dip. As you began to make that top surface higher in terms of its curvature, in particular, 1 diopter being the lowest and 3 diopter being the highest, what happened is you got rid of the spurious response over here. You didn't have all of this low-level response associated with the planar, and lo and behold, you got a very strong impedance this is the normalized frequency, which is the frequency of the device divided by the transverse shear mode resonant frequency, and you get a very clean spectrum over here. Similarly, over here on the phase, you got rid of these two, and you ended up getting a very clean spike, again, at the appropriate point. So basically what we found is, yes, you can excite that transverse shear mode. You must be careful in terms of the orientation of the electrodes, that the actual electric field is perpendicular to the electrode spacing, and finally, make sure that it is planar convex. You might say, well, why don't you go higher than 3 diopter? Why don't you go 4 and 5? Too much of a good thing. What happens is it focuses the energy almost to a point, and the actual active surface sensing area has decreased. So what we found was 3 diopter was the optimum curvature. Well, how does that work? All right, here is the frequency changes of a group of sensors. This is the lateral field excited sensor with 1.5 gap, 2 gap, 2.5, 3.5, and now the open ring, small ring, closed ring, etc. And finally, the standard QCM on all of these. This is the gap. You see, this is the standard QCM, I, right up here. Responding to concentration of sodium chloride, it could care less. Basically, a conducting solution, the thin film basically shorted it out. So it was incapable of measuring that electrical property. H, E, F, and G all correspond to some of the modifications that we looked at, in particular, open ring, small ring, closed ring, and so forth. And finally, this group down here, and this group down here was the lateral field excited device. A, B, C, and D corresponding to different spacings in terms of the gap. You see here 1.5, 2, 2.5, 3.5, and the best one was 1.5 millimeters in terms of the actual gap. You have to be careful. If you make the gap too small, your sensing area is too small. If you make the gap too big, the strength of the signal goes down significantly. We then continue to ask the question, well, what about another electrical property? And that electrical property is permittivity. Those of people who are familiar with dielectric constants realize that's a dielectric constant of water. And as you add 2-propanol solution to that, what happens is you get a change in the permittivity. Here what you see is the standard QCM represented as F. And now these three here, corresponding strictly to the LFE for A, B, C, and D and E are the open ring geometry kind of grouped together. And again, you see the bigger changes occurring in the corresponding LFE structure. And finally, we said, well, what about viscosity? This is one that surprised us a little bit. Viscosity is a mechanical property. And we figured that, well, the LFE probably is, equal to QCM, but we didn't think it was going to be superior to it. Well, here are the results. What you see here is the standard QCM in G, right at the top. And then F, A through F corresponds to the LFEs of different spacings and even the open ring and small ring geometries, which I gave figures on earlier. And you see that of all of those, again, the LFEs are grouped together, and this one right here, the A group, has the biggest shift. Now the question is, why did this thing also respond better than the QCM? Well, the QCM has got this gold layer on the top. And that gold layer helps to shield the measurements of the viscoelastic properties. So the actual material, in this case a water glycerol solution, the actual acoustic energy has to penetrate through the gold to get to it. On the LFE, it doesn't need to do that. The LFE surface is bare. So the actual penetration is directly into the water glycerol solution. All right, what about an equivalent circuit for this so-called liquid-loaded quartz LFE sensor? The equivalent circuit for the QCM is reasonably well known. The equivalent circuit basically consists of a capacitor because it's got metal top, metal bottom, and then on the parallel arm, it's got a capacitor, resistor, and inductor. The resistor deals with measuring the viscous effects of the acoustic wave propagation. The capacitor and the inductor basically correspond to energy storage elements. So on the equivalent circuit, what we did is we decided we were going to look at trying to determine the equivalent circuit from the LFE sensing platform. Theoretically, this was not an easy problem. I'm not going to go through and bore you with the mathematical details. I'll show you some of the steps. The assumptions, the approach we took, the equivalent circuit that we ended up getting, and the experimental results. You had to solve the coupled acoustic wave equations and apply the appropriate boundary conditions, derive an expression for the admittance or the impedance. Whoop, go back here. Derive these, once you've got the impedance or admittance, derive the circuit elements based on the admittance that relate to the material properties of the crystal and or liquid. Here's the geometry. Again, this is the theory. Here is the quartz. There is the electrodes on the bottom. This represents an LFE type structure. There's the liquid on the top. And this is the side view. This is the bottom view looking up. And you see the two half-moon structures given over here in various dimensions associated with that geometry. The assumptions we made, only simple thickness shear modes are considered. Displacements, again, transverse to the direction of propagation, which is in the x2 direction. Displacements in the x1 direction. Plane is considered to be infinite in the x1 and x3 directions. Applied electric field is in the x3 direction, lateral applied electric field. And we use the quasi-static approximation. What is a quasi-static approximation? You're talking about piezoelectric materials. If you're talking about acoustic wave propagation in piezoelectric materials, you really should be looking at the set of Maxwell's equations plus the Christoffel equations. We have done that calculation, and it turns out that the difference, the results you obtain between quasi-static and full-blown Maxwell treatments is very, very small, and quasi-static approximations is a heck of a lot easier. Without boring you, here are the system of equations. This corresponds to the piezoelectric material. This is the solution. This corresponds to the corresponding liquid, so-called Navier-Stokes equations. Here are the solutions to it, and here are the various quantities defined. The equivalent circuit, we basically developed the equivalent circuit, and it consisted of course, some sort of a capacitor here, and this other arm was a little bit more complicated, whereas in the standard QCM, you just had resistor, inductor, and capacitor. Here you had a whole separate set, and in fact, you had 8 different equivalent circuit elements. What are they? Well, here they are right here. They are given in terms of some of the fundamental parameters associated with the problem, such as density, liquid viscosity, quartz viscosity, permittivity, conductivity, and so forth. So all of these elements are basically determined by the geometry and the physical structure of the lateral field excited device itself. So the next question, how does it compare to experimental results? Well, this represents a measurement of the admittance using a network analyzer as a function of frequency. This corresponds to the peak here. This is admittance, so this corresponds to 1 over impedance. This is the location of that transverse shear mode, somewhere around here in frequency. The experimental data is given by the curve you see here. This is almost indistinguishable. And there's the model data right there. So what it basically means is that this equivalent circuit that you have in fact obtained through the solution of these coupled equations appears to agree reasonably well with the experimental results. What about the phase? First one was a magnitude. This is the phase. And again, there is the corresponding frequency, the TSM frequency. Experimental data. A little bit of deviation over in this region here, a tiny bit over here, but otherwise a very good representation. All right, with that, then what about the conductivity of the response of this sensor in terms of sodium chloride solutions, okay? Here we look at the, and this is theory versus experimental results, whereas what I gave before was basically experimental results. This is the theory, the solid line model, and this is experimental data, which indicates that, although we're not exact, we've probably got a decent handle as far as what the equivalent circuit representation looks like. The next slide is the results for the isopropanol solutions, which is the corresponding dielectric constant. Again, water over here. This is the change in frequency. Again, the measured values and the model values, again, indicating decent results. This corresponds to viscosity. The measurements are fairly broad in terms of the experimental measurements, but the general trend seems to be, in terms of the theory and the experiment, to show somewhat of a correlation in terms of the results. All right, the conclusions are the equivalent circuit. On the equivalent circuit model has been developed that appears to reproduce the admittance of the LFE sensing element under deionized water loads. Expression for the admittance obtained on the model at or near resonance has been derived. Equivalent circuit predicts the frequency shift with an experimental error due to viscosity, permittivity, and conductivity changes on that surface. Okay. So the next question is, well, how does it work in terms of real entities? Being an electrical engineer, I know a little bit about the acoustic wave platform, but trying to apply this to a real-world scenario has to require a little bit of work in terms of trying to determine what should I begin to try to utilize this sensor to detect. And what we chose to utilize it for was the detection of phosphate, which is the short for organophosphonate that's used in fruits and vegetables. And if consumed in a significant amount, it can cause some serious problems as far as health is concerned. In fact, we had a faculty member in our department who originally came from Brazil, where there was no real limitations in terms of spraying. His entire family got sick from, believe it or not, eating bananas. Don't ask me how that phosmic got through the banana outside, but basically they were all taken to the hospital and they ended up surviving. But it basically had to do with high concentration of phosmet. We also have to ask the chemists, what kind of film are we going to utilize in order to try to attract phosmet? And the film that was suggested to us was, I'm not even going to pronounce it, it's PECH. You can read it. And these are the results that we got. This was the frequency shift. This is the shift from the transverse shear mode frequency as a function of injections. This is in the LFE, 1.34 parts per million in the injection. And here are injections in 10 microliters, another 10 microliters, another 10 here, and another 10 here. So we're getting more and more concentrated. And this is quartz, 1.49 parts per million, higher concentration on the quartz injection. And this is the results for quartz, and this is the results for the LFE. I mean, the QCM here and the LFE here. So you're seeing, in the case of the LFE, less concentration and a bigger shift than what you see in the QCM. So we then decided that we would go to the detection of, I thought I wrote it down. I guess I even didn't write it down. Yeah, I wrote the acronym over here, STX. The acronym stands for Saxitoxin. You might say, what in the world is Saxitoxin? All right. Saxitoxin, if you talk to the people in the Department of Defense, they will recognize it as being one of the most dangerous of all natural occurring neurotoxins. They are of extreme interest to utilize, I don't want to say utilize, but to know what they want to know about this particular material. Now, the question is, how does Saxitoxin form? Well, what happens is periodically, and this is along the northeast coast, along with other coastal areas, you end up getting an algae bloom. And that algae bloom will appear as a red algae on the surface of the material of the bay area or areas where clams and mussels may reside. What happens is after the bloom, the algae will precipitate and go to the bottom. And when it goes to the bottom, it ends up getting consumed by bottom-dwelling individuals. And the bottom-dwelling individuals are, to a large extent, mussels and clams. Once it gets consumed by the mussels and clams will form this neurotoxin called Saxitoxin. If you end up consuming a mussel or a clam that has Saxitoxin in it, chances are that you're going to become ill or you could die. There was a very unfortunate incident about 6 or 7 years ago on the Maine coast, and this had to do with an area down near Eastport, which is the far eastern part of Maine, where a clammer, it wasn't a clammer, it was a lobsterman, had picked up a barrel, or I think it was a barrel he picked up, that had a large number of mussels on it. And he took the barrel home and harvested the mussels off of it, not knowing where the mussels or the barrel came from, and ended up feeding it to his family. The unfortunate result was his entire family died. Those mussels were infected with Saxitoxin. You might say, okay, then how do you detect Saxitoxin? The detection of Saxitoxin is incredibly rudimentary. What they do is they take mice that have been very carefully cultured, and they feed the mice Saxitoxin. And they observe, I shouldn't say feed, they feed the mice the ground up clam tissue, and they observe the mice for a period of 2 or 3 days and see what happens. If there's nothing that happens to the mice, it means the area isn't contaminated. If the mice dies, then the area is contaminated. and most likely has saxitoxin. That is the state of the art as far as the detection of saxitoxin is concerned. Now what they do is they see red tide, they immediately close the clam flats. And in the last 2 or 3 months, there have been several clam flats, at least along the Maine coast, that have been closed. So what we did again is we contacted people in the area of chemistry, and this is the god-awful thing that they told us to utilize that would selectively detect saxitoxin, all right? We said, fine, go ahead and create that film for us, and they went ahead and they created that film for us. A graduate student published this particular paper and also presented it at the IEEE Ultrasonic Symposium. I think it was 2007, 8, 9, somewhere in that time frame. And this paper won the Best Paper Award. Here you see the response. This is the frequency associated with the actual quartz device. And at this point in time, here's the injection of saxitoxin, and here is the response, and there's the final frequency. I should point out it was no joke trying to get a sample of saxitoxin. We had to pull some strings in order to get that. Again, a very dangerous neurotoxin. Biological sensing. The entity that we were looking at here, E. coli, 015787. Anybody in the area of biology will realize that this is one of the most dangerous of all E. coli. This particular strain was first uncovered in the early 1990s when a young kid in the Midwest was eating a hamburger at a Jack in the Box restaurant. And the Jack in the Box restaurant, basically, the hamburger had E. coli in it. Where does E. coli come from? Everybody in this room has all kinds of E. coli in their system, all right? This is the bad one right here. Basically, it comes from droppings from animals such as deer, animals such as cows, etc. And often the droppings, sometimes they get mixed in with water and they're used to wash out spinach, or unfortunately, sometimes they get ground up into Hamburg. And finally, be careful when you drink cider that's not pasteurized. What happens with the cider is underneath an apple tree, you've got all these apples, and the farmer goes ahead and harvests the apples. Most likely, they've been deer that have been eating those apples. And if those deer have been eating those apples, there's probably droppings around them. Make sure that those apples are washed and make sure they're pasteurized. Cider not pasteurized can give rise to some serious problems. The film, bioreceptor film, here you see it. It consists of amines, biotin, avidin, and then an anti-E. coli, which is attractive to the E. coli that we want to detect. And here is the response. It's a complicated response. This consists of the various biological entities that go into the film. At this point here, it's exposed to the dangerous E. coli, and what you end up seeing is a gradual change in the response that looks like this. This basically, we think, has peroxide-based explosives. Peroxide-based explosives can be made very simply by adding 3 components, and I'm not going to indicate what those 3 components are. Unfortunately, you can look them up in the literature, together, and those 3 components, when they're mixed together, will outgas 2 gases. One of those gases, the outgas, is acetone. And this represents a sensor that we had developed. This is in collaboration with some polymer chemists. This is a polymer type sensor. Here you see the LFE signature. The analyte is introduced right here. You see a very quick response. The analyte is removed, and then analyte is reintroduced, and you see again that it's responding. This is the 60 parts per million of acetone. And here is the 0 parts per million of acetone, no response at all. And the film is given over here. It's the siloxane fluoroalcohol. And this represents even more dottering associated with that polymer film. This was done in dry air. That's for acetone. We looked at a couple combinations of films. These are 2 different films, prepared very similar base and different types of additions here. And this is, again, detailed in publications that we have, the blue one representing one and the dark one representing another. And then finally, well, what about H2O2? What about hydrogen peroxide? Very similar kind of a representation. Analyte introduced. Here's the change, removed, and here's the change against reproducible. This is the 12% hydrogen peroxide vapor. This represents the 0%. So the basic thing here is that if you got a candidate person that you are suspecting might be troublesome, and you end up picking up hydrogen peroxide or acetone, you better remove that individual from wherever he's heading. This represents here 2 polymer films. This is again to change to hydrogen peroxide, and you see that both of them respond. So let me move on to what about other crystals for an LFE sensor? Well, the candidate material should have a pure transverse shear mode. It should be able to selectively excite that pure transverse shear mode. That transverse shear mode should be temperature compensated and should exhibit a high piezoelectric coupling. That motivated us. This is the standard crystallographic orientation. The key angle here to be concerned with is the angle psi. I should say psi, not psi, phi and theta. This represents the angle on the face of that piezoelectric material. In this case, it's lithium tantalate. And for this particular representation, the psi angle necessary on this one is the psi angle over here, where you're exciting nothing more than the transverse shear mode here. And this represents 2 different cuts, minus 16.5 degrees and a minus 83.4 degree cut, both giving rise to a temperature-compensated shear mode. There's the velocity of the mode. We had a choice of choosing this one or that one. We decided to choose this one. You might wonder why. No potential interference with this one, or not as much as might occur in that one. Notice the coupling here, 40, 45, and so forth. For quartz, that coupling percentage was 5 and 6. You're talking about 6 to 7 times more sensitive to the excitation in the case of lithium tantalate. How does it work? We thought reasonably well. Here's the response to sodium chloride, AT cut, fundamental quartz. That's given on the top as the AT cut. LFE and the QCM, they seem to be virtually one on top of the other. This is the lithium tantalate one. Look at these changes. These shifts are huge, all right? Now let's look at this region exploded. This region exploded. Here is the QCM. Here is the LFE device, all right? Much more sensitive, now using an LFE device that's on lithium tantalate. How does that work in the case of the 2-propanol solution for the dielectric constant? Very similar representation. Significant changes over here occurring. These are LFE and QCMs. Over here, you see the corresponding QCM expanded scale. Oh, this is a shrunk scale or expanded scale in this region, and here's the LFE over here. This is in the case of viscosity, not quite as dramatic, but still significant in terms of this is the expanded scale. This is lithium tantalate. This one over here is the quartz, and this corresponds to 2 harmonics on the corresponding lithium tantalate one with the LFE. So conclusions for the LFE sensing platform: it offers advantages over the other bulk acoustic wave platforms, and in particular highlighted in terms of the so-called bare sensing surface. Electrodes are only on the reference surface. This enables us to detect electrical properties, which cannot be done with the QCM. It's more sensitive than the QCM in all three cases. These two understood. This one a little surprising. Senses chemical analytes, phosphate, saxitoxin, biological entities, sensing vapors from peroxide-based explosives, and we can use other piezoelectric crystals. What about future work? What about identifications in other piezoelectric crystals for LE sensing platforms? You might want to say, well, what are some other piezoelectric materials that might be temperature compensated and can be utilized? A material called langasite in the lanthanum group, which exists in single crystal form in excess of 1,000 degrees. It can be utilized to determine properties or senses in a very, very hostile high temperature environment. What about the utilization of piezoelectric films, such as aluminum nitride and zinc oxide as this LFE sensing element? This thing can be made in the order of 1 or 2 microns thick, whereas the other ones are on the order of millimeters thick. Quite a difference. Very, very thin films means very high frequencies. Instead of talking about devices that operate in the 10 to 20 megahertz region, we're talking about devices that operate up into the gigahertz region. Real-world operating systems which utilize LFE sensing elements. What about a actual handheld device? Development of an LFE-based sensing array. And what about the development of a new class of acoustic-based sensing elements which use antennae as excitation sources? You've already seen one with a helix-type representation, the helical coil. Certainly, there is an innumerable number of antenna configurations that you can realize. The aluminum nitride or zinc oxide configuration, this represents the liquid sample. This is carved out of silicon. This is an SiO2 layer that's used to add temperature compensation. There's the tiny aluminum nitride. There's the 2 gold things, and there's the PC board that holds it up. This is the top view, and this is the bottom view. This is potential LFE, ALN biosensing platform, which we think would be extremely interesting in terms of looking at very, very low concentration analytes that might be present, for example, in biomarkers associated with cancer and things of that nature. Further, this is a COMSOL calculation of the electric field between the electrodes, 15 micron gap width. This is on aluminum nitride, and you see the electric field here is primarily in the direction horizontal, which is what it should be. And here is the electrical density between the electrodes, and red being the highest density, indicating in terms of the energy. This represents an actual conceptual drawing. We're in the process of interacting with a company in the Boston area. This represents a vacuum system. This is a metal target over here, and this represents some sample holder of a device that you want to deposit. You might be interested in the thickness of the film, but you might be also interested in the electrical properties of the film. This is an LFE device that's on it inside. This is then connected to a signal processing unit, and that represents a commercialization concept of a replacement of the QCM monitor with an LFE monitor. Finally, what about the possibility of more than one sensor on the substrate? This indicates a whole sequence of sensors where this thing has been exploded, and it looks something like that in terms of a side view. And here represents some of the powder blasting to get that trench structure on the top. And this represents some experimental measurements. This is an actual element. This is an element adjacent to it. The trench structure separates the acoustic energy from going from one structure to the other. So you've isolated now a single device, and this one represents yet a second one using that particular structure. And finally, this represents some potential antenna configuration, 2 dipole antennas. This is the actual device here, which is between them. This here represents the device separated on top. This represents a device in a side view. This represents a device in a horizontal view. So again, those are areas that we have looked at briefly and are continuing to look at. But again, it all basically is based on the lateral field-excited device, a device that we think has some potential as far as sensing is concerned. One final comment, and I've mentioned this to several people that I've talked to, is being an electrical engineer and having little or no access to a medical facility, detection of analytes, such as biomarkers for various kinds of diseases and so forth, be they in gaseous form or be they located in a liquid environment, would certainly be of interest to us to look at. What we don't know, of course, is what those biomarkers might be, and secondly, the actual film or entity receptor film that's going to be able to capture those biomarkers. And we definitely think that not only the conventional LFE using quartz, but the LFE with lithium tantalate, and most certainly an LFE associated with a material such as aluminum nitride would have some particular promise. So I thank you for listening to me, and if anyone has any questions or any comments, I'd be free to entertain them.
So you mentioned putting multiple sensors on it. I think of lots of good reasons. One, I'm wondering if you could look at the different signals, sort of, even if you didn't have perfect temperature calibration, use a different signal between two sensors to compensate for temperature. But perhaps more generally, would you have many, many different sensors and look for a signature for a given element?
So what are you you're talking about? Basically, putting an analyte which might consist of, or a fluid or a gas that might consist of more than one analyte in it, and then have each one of the sensors designed to detect a particular analyte.
Almost an artificial nose sort of environment.
Yeah, certainly you could do that. Yes, yeah. It's a question we ran into on this was. In terms of the actual device, was to try to dig these trenches and to try to make sure that these trenches acted as dividers so that the acoustic energy didn't go from where we wanted it to go and go to the one right next door and give rise to interference. That's what we were concerned with.
Did you also look at differential signals?
Yeah. John?
So I have this classical question. If you look at, of course, crystal microbalance and this type of acoustic sensors, the damping play a significant role in biosensing. In biosensing, you have sensors in the liquid environment. When you have a liquid environment, the quality factor will be very different compared to vacuum. So do you see any of these factors play a role there when you immerse LFE in liquid, especially in viscous liquid?
Well, our interest in terms of LFE is, we looked at liquids and you saw the development of that equivalent circuit representation. But that liquid could have finite viscosity associated with it. It would affect the equivalent circuit, and as you might expect, it begins to, approach, from an ideal liquid to a solid. You have that transition region there. And we have not looked at two solids, for example, because we can't find a practical problem in terms of introducing an analyte into a target analyte into a solid. But as viscosity increased of the liquid, we could have some problems in terms of attenuation. We haven't looked at that in detail. In other words, we haven't looked at different viscosities in terms of the LFE and a biofilm on the top. What we'd really like to do is we really like to identify a biological system, in other words, a particular analyte, be it in a fluid such as sweat, urine, blood, or what have you, and then begin to try to, see what kind of results that we got. Often what happens, and people have looked at biomarkers, and they have looked at them using QCMs. LFE has not been used. And, of course, the QCM is fine. In fact, you're just interested in change in mass or a change in the viscoelastic properties. But if your bioreceptor film has absorbed that target analyte and it's changed its conductivity or its permittivity, you're not going to pick it up. And my guess is that when you're looking at these biomarkers is that you've got some polarizable molecules in there. And the fact that you have that is, my feeling is that you're going to get some significant dielectric property changes. We would like to certainly try it, and anyone here has any candidate systems that they want to suggest, we would certainly be willing to collaborate in terms of taking the films and the analytes, and we would, obviously design and fabricate the LFE device. You can do the testing here or do the testing at Maine. Yeah.
As you talked about earlier, the key is the specificity too, and the sensitivity. So for like the toxin, the marine toxin problem, how close does the sensor have to be? Is that in physical contact with the plant, or is the toxin?
No, what we do there is, we take the actual clam meat and we grind it up and make it into a slurry. And that slurry basically is more or less in quotations, a viscous fluid. And then we place that on the top. As I indicated in my talk, the amount of work that's been done on the whole area of the detection of this material, Saxitoxin, is very rudimentary. And just think that you feed it to a mouse and you decide how long is the mouse going to live, and depending on how long that mouse lives, determines to a certain extent the concentration. And if he dies quickly, it means that the concentration level was quite high. If he hangs around for a while, then probably wasn't as high. But to my way of thinking, here is one of the most dangerous naturally occurring neurotoxins, and this is the way we use to detect it. Going back, and I've spoken to several of the people in terms of detection of gases using metal oxide films, I think I might have pointed out that that began to come in the forefront in the 50s and the 60s, and in particular, what did they use before that? Before that, they used all kinds of crazy things, going way back, a canary in a cage type of a thing, and then some of the early methane sensors, which were very large and cumbersome. But what happened was a Japanese fellow by the name of Takuchi in the 1960s was a mine worker. And he basically was working in a mine, and there was a methane explosion and ended up killing several of his fellow workers. And he became absolutely fanatical in terms of trying to develop a sensor that would work. And he had some idea going back to some rudimentary work that was done in the 1950s and also even into the late 1940s when Bardeen Shockley and so forth looked at the doping in silicon in terms of looking at the changes in the properties, that he thought that maybe a film such as SiO2 or a metal oxide film might work. He went through the entire periodic table. It took him 10 years. And he finally came up with a combination of a tin oxide, a doped tin oxide film to detect methane gas. He had one publication. It was a patent. He was then bought out by Figaro, and if any of you go ahead and Google Figaro, you'll find out it's the most well-known company in terms of making thin film gas sensors. So that gives you an idea how some of these things, come about.
Thank you very much.
Okay.